Hello everyone, I am Vishak Chandra Ghosh from IIT Kharagpur, and here I am presenting our work Decentralized Cross-Network Identity Management for Blockchain Interoperation. So permission blockchain technology is having a steady growth in its popularity over the last few years, and now there are several examples of its adoption in the enterprise scenarios. But there has been an industry trend to create these enterprise networks as minimum viable ecosystems with the minimum set of participants required to demonstrate short-term goals. As a result, these networks have emerged as isolated silos in different spaces such as trade finance, trade logistics, provenance, etc. And often these different networks are being built with different blockchain technologies and platforms. But there is a need for interoperation between these networks to achieve several business goals. And by interoperation, it can be in the form of asset transfer or asset exchange. But in this work, we are particularly focused about verifiable data transfer from one blockchain network to another permissioned network. A work by Abebe and others proposed a solution for this verifiable data transfer between two permission networks, and this is based on relays and proof by attestation. So the key idea here is that it supports multi-party trust. That is, when one network is consuming the state from another network, it would need to establish the validity of the state according to the shared consensus of the parties in the source network. So first, one network queries for some data from the other network, where the query is first validated against some access control policies, and then the data is attested with signatures by the participants of that network, after which this data along with the proof is sent back, and in the requesting network these attestations and signatures are validated. But of course, in order to do this validation, the identity configuration is required. So the public key and the certificates of the participants of the source network is required. Permission networks have their own private and proprietary identity providing mechanisms which certify who belongs to the network and thus limits the memberships in it. So any kind of proofs, and especially the attestation proofs, rely on the knowledge of the identities in the counterparty networks. But this access or exchange of participant identities across the networks is beyond the scope of the existing blockchain technologies and as well as the interoperation mechanisms that have been proposed earlier. Therefore, the objective of our work is to design a secure distributed identity management infrastructure with a set of protocols for linking the permission networks, which then can be used for interoperation. So there are several challenges of designing such an identity management system. Firstly, the identity of the participants are closed within the permission blockchain networks and they do not have any manifestation outside the network boundary. Apart from that, here we have to take care of different heterogeneous blockchain technologies which have different identity management systems as well. Therefore, they might have various cryptographic algorithms and data structures being used for identity management. Apart from that, there is lack of common identity infrastructure, so there is no central identity providing authority. Then we have to take care of security, where we have to prevent any non-member to pose itself as a member of a network. And then the identity configuration in a particular network has to have consensus by all the participants in the network. We focus on several design goals while developing our system. Firstly, the system has to be DLT agnostic, so our system should not be tied to any specific distributed ledger platform such as Fabric or Corda. Then the system should not have any central identity register and it should be completely decentralized. Apart from that, the networks must remain autonomous. So the networks that will be using our system should be able to choose what identity providers they are using which trust anchors they trust, etc. And finally, this is very important that our system should be implementable with minimal change to the existing code and configurations to the already deployed networks. Coming to the overview of our solution, we considered the interoperation functionalities of verifiable data transfer with the proofs and attestations in a separate plane called the data plane. So this data plane is concerned about the data requests and proof validation. And then we separate out all the identity management functionalities in a different plane called the identity plane, which is concerned with the exchange and configuration of identity among different networks. The first step towards building this identity plane is decoupling the identity of the participants from the network. So the blockchain network specific identities are confined within its network boundary. For example, in Hyperledger Fabric, the Fabric certificates of the participants are specific to the network and are not manifested outside the network boundary. So for identity exchange, this identity must be platform agnostic and it also must be decoupled from the network so that it can be made available outside the consortium boundary. Therefore, we use the concept of self-sovereign identity or SSI in the identity plane, which allows us to decouple the participants' identities. So even though inside the network, the participant will have the blockchain network specific boundary, it will use the SSI for identity interoperation in the identity plane. For interoperation, the configuration and validation of SSI is not enough, and there is a requirement of different identity mappings which has to be validated also. So firstly, the real world identity, which for example can be the companies or organizations which is participating, its name, address, etc. Then from the real world identity, the validators must be able to verify its network membership. So this is the proof that the subject of an SSI is a participant of the concerned network. And finally, there is the blockchain network specific identity. So this is the cryptographic keys and certificates which are being used within the blockchain network by the participant. This is required because ultimately in the interoperation step during verifiable data transfer, these keys and certificates will be used to sign and attest the data. We are using these building blocks in our system for SSI and providing the basis for the identity mappings. We are using decentralized identifiers or DIDs, which are digital identities, SSI independent of any registry or provider. And then we are using verifiable credentials or VCs, which are digital credentials issued by the issuer to certain DID subject which becomes its holder, and these VCs attest to claims about the holder which can be verified by anyone without the involvement of the original issuer. So both the DID and VC specifications are W3C recommendations. And apart from that, we are using verifiable data registry, which is required to support this VC data model. The verifiable data registry contains certain information such as schema of the VCs, authentication keys of the issuers, revocation lists, etc. For our use case, this verifiable data registry also must be decentralized, and therefore we have to use a DLT based implementation. So we use Hyperledger Indy, which is one of the most advanced implementations of such blockchain based VDR for our use case implementation. Our system has to be completely decentralized, and hence it does not depend on any central identity provider. Instead, it relies on trust anchors, which act as basis for identity validation and mapping between the different types of identities. So we categorize these trust anchors into two. The first one is organization identity validators or OINs. These OINs associate SSIs to their real world identities. So deeds by default are not associated with any real world identity, and we consider the OINs as trust anchors with already well known real identities. So these OINs can be relied upon to associate other deeds with real identities. And the second type of trust anchors are participant membership validators, or PMVs. So these PMVs associate a real world identity to network membership. So basically, the PMVs validate the membership of a deed owner in a particular permission blockchain network. These PMVs are trust anchors that are well-known representative of that network, and hence can attest the participation of others in the same. For example, IBM or Walmart both are reputed entities of the IBM Food Trust Network, and hence they can act as PMVs for this, and they can attest the participation of others in IBM Food Trust Network as well. But ultimately, the choice of the trust anchors entirely depends on the network and its participants. This is the identity plane architecture that we have proposed. So in the identity plane, there is this interoperation identity network, or IAN component, which is formed by a set of trust anchors, both organization identity validators and participant membership validators. And apart from this pool of trust anchors, there is a DLT-based decentralized verifiable data registry, which is used for storing the real-world deeds, auth keys, PC schemas, and revocation lists. So in our system, there are multiple such IANs which together form the distributed identity infrastructure. And this cloud of IANs acts as the basis for identity validation and identity interoperation in this identity plane. So the blockchain networks have a component called IAN agents, and each participant in the network has at least one IAN agent, which is used to communicate with the IANs. And these IAN agents form the network identity managers of the network. And also the IAN agents communicate with each other to sync the foreign network identity, credentials, and certificates. Then the data plane functionalities of verifiable data transfer goes on as usual, using the identities which are configured by the IAN agents in this identity plane. The primary mechanism that we need to support in the identity plane is the addition or modification of a participant member of a network, whose identity and certificates are then need to be synchronized and validated into another network. So this can be used for addition, modification, as well as removal of participant members in a network. So let us go through an example flow of the cross-network participant validation protocol, where let us say that network 2 wants to configure the identity of org3 of network 1. And here this IAN with one PMV and one OIN and a verifiable data registry is commonly being used by both network 2 and network 1. First, org3 configures its own identity by initializing a real-world deed with the help of OIN, which registers the real-world deed in the verifiable data registry. And then the PMV issues a membership VC for org3 into network 1, which configures the membership identity of org3. And then finally, org3 issues a self-signed VC for the platform-specific certificates. So with these three steps, the SSI of org3 is mapped with its real-world identity, its network membership, as well as the platform-specific certificates, which will be used for interoperation. Next, org2 validates the identity of org3 by first validating its real-world deed from the verifiable data registry, and after this, it also validates its membership identity by verifying the membership VC through a verifiable presentation. And then it also checks the verifiable data registry's revocation lists to ensure that none of the credentials have expired. After this, it fetches and validates org3's platform specific certificate. So at this point, Org2 has successfully validated Org3's identity, its SSI membership, as well as the platform specific identity. Any participant cannot update the identity configuration in the network by itself, and instead it requires the consensus of all the participants in the network to do so. So to update the identity configuration of Org3, Org2 first sends a request for collecting signatures over the identity configuration. Here it sends a request to Org1. Org1 validates the identity of Org3 and puts its signature for attestation over the identity configuration and sends it back to Org2. So in this way, Org2 collects all the attestations from the network participants and sends a transaction to the consortium smart contract, where the smart contract validates the signatures of the participants and updates the identity configuration in the ledger. We rely on this kind of application level flow of getting signatures for consensus over the identity configurations instead of doing it in a smart contract, because the identity validation steps involve many network calls which might introduce non-determinism, and we want to avoid non-determinism in the smart contracts. We have done a proof of concept implementation of our system with two Hyperledger Fabric networks, and we have implemented the IAM agent in the identity plane as a module of the Fabric CA, which is responsible for managing the identities of participants of a Fabric network. This IAM agent is implemented with the Hyperledger ADs toolkit. Apart from that, the IAM itself is implemented with Hyperledger Indy forming the verifiable data registry, and the set of trust anchors are implemented using Hyperledger ADs. So the different IAM agents communicate with each other to exchange VPs for membership credential and Fabric certificates, and then the IAM agents communicate with the ledger through peers with the help of IAM Fabric client. So the IAM Fabric client is also responsible for executing the signature collection application level flow before submitting an identity configuration in the ledger. We have tested our implementation with the simplified emulation of two real-world networks. We built miniature scale versions of the networks using Hyperledger Fabric that are loosely inspired by the real-world networks Tradeless and VTrade. So VTrade is a trade finance network and Tradeless is a trade logistics network. In the real world, shipments may require the proof of letter of credit, whereas the payments require sellers to produce a valid bill of lading. Here the trade finance network, VTrade, manages the letter of credit, while the logistics network, Tradeless, manages the shipping consignments and bill of lading. Thus, the two interoperation steps required is the verifiable transfer of this letter of credit and the bill of lading. This forms the data plane, and we have used our Hyperledger Indy based implementation of the identity plane with two example trust anchors, IBM and Maersk, and this system successfully configures the identities of the participants across the two networks. To conclude, we have introduced a decentralized identity management plane for facilitating interoperation, which is DLT agonistic and based on DID and VC concepts. So this system requires no changes to the existing DLT platforms, and only some additional smart contracts and application layer implementations are required. In future, we plan to extend our protocol for network formation and discovery without trust anchors, and also do the implementation with Corda and Besu. And apart from that, we want to carry out performance evaluation of our system. So thank you, and looking forward to your questions.